Welcome to Math 108. Today we're going to talk about functions and function notation. So a function is just a mathematical relationship between quantities. For example, in economics, you might be interested in how price affects demand, right? The relationship between price and demand. In physics, you may be interested in the force required to move an object given the mass of that object. Or say in the medical field, you might be interested in the quantity of a drug in someone's bloodstream as a function of time. You want to know how it varies over time. So these mathematical relationships are very useful, and there are four main ways to describe a function. So here we have a description in words, right? The area of a square is the square of its side length. So that's a description of the relationship between the area of a square and its side length. So we also have a formula here. We have a is equal to x squared. Now this is actually saying the same thing as the words. Okay, if we let a be the area, right? So now I'm just, instead of saying area, I'm saying I'm just using the letter a, but it represents the area of the square, and x represents the side length. Okay, so this formula is saying the same thing. Area is side length squared. Okay, the area of a square is the side length square. So now if you're given the side length, if you have a measurement for the side length of a square, you can compute its area. All right. Now we can also give a function in terms of a table. We can describe a function in terms of data. And sometimes some relationships, that's all you've got. You've got some data, and you can look at the relationship between two quantities. In this case, it's a square. there's a pretty straightforward formula, but sometimes there is no formula, and you're just given data. And so, but this describes a relationship between x and a, right? The side length of the square and its area, just given as a table. And then finally, we can actually represent it as a graph, right? So we can put one variable on the horizontal axis, right, and the other on the vertical axis. In this case, we put the side length on, so this represents side length down here, on the horizontal axis, and then area is on the vertical axis. So this is area up here. And now we can, if we want to know what the area is for a given side length, of course, within the, within the range that's graphed here, we can just read it off of the graph. So for example, if we know we have a side length of 2, I can find 2 down here on the x-axis, and then look and find the point on the graph, and that corresponds with a side length, or sorry, an area of 4. Okay, same way here. If I want the area for a side length of 4, then I can see, okay, just go straight up to the graph, find the point on the graph, and find its corresponding value for area, right? So the nice thing about the graph, though, is that we can also estimate values between. So if I wanted the area for a side length of 3.5, I could just find, approximately where 3.5 is, and look at the corresponding point on the graph and see, oh, okay, it looks like that's about 12. It's a good estimate. It's 12 square centimeters if we have a side length of 3.5 centimeters. All right, so let's take a look at example 1 now. Here we're just asked to describe the relationship between the circumference of a circle and its diameter in words, in a formula, a table, and a graph. All right. So I think I might actually start with the formula, because if you remember from geometry, circumference is equal to pi times the diameter. Okay, so here I'm letting C be the circumference, and I'm letting D be the diameter. So this is just sort of a shorthand way, right? It's a nice, concise way of expressing the relationship between circumference and diameter. So instead of having to write out circumference and write out diameter, I've got symbols, right? I've got C representing circumference and D representing diameter. So if you give me a diameter, now all I have to do is plug it into this formula and I can calculate the circumference. Now in words, what this is saying is that the circumference, whoops, I can't spell, circumference of a circle is pi times the diameter, right? The diameter. Now that's a lot more to write out, right? That takes a little longer to write. That is the relationship. It's just it's saying the same thing as C equals pi d, only it takes a lot more. It's in plain English, so it's more understandable maybe, but it's a lot more words. And the formula is a nice, concise way if you know what all the symbols mean. It's a nice, concise way of expressing the describing the relationship. All right. So now we can also take this relationship and show it as in a table, right? So I could basically plug in these diameters and get the corresponding circumferences. All right, so voila, there it is. All right, so pi is an acceptable number. Pi is a number, but sometimes it's a little nicer to show that as a decimal approximation. So this 3.14 is actually an approximation of the circumference of a circle with a diameter of 1. Okay, so these decimal numbers are all approximations. The exact number would be in terms of pi, right? So pi, 2 pi, 3 pi, 4 pi. All right, so there we have the relationship shown as a table. All right, so lastly, we can also show this as a graph. And now that we have a table, it's really easy just to plot those points. So for well, let's see. First of all, we have to decide how are we gonna use these axes that we're given. Now, given the scale that I put on these axes, it's kind of obvious that this has to be D. Oops, hang on. D. This has to be D, and this has to be C. But when you have the circumference written as a function of diameter, then diameter is the input, right? It's the input. If you give me a diameter, I can just directly calculate the circumference without having to do any algebra or any finagling, right? So it's the input, and it's also sometimes called the independent variable. Independent variable. Okay. So here we've written a formula for the circumference as a function of d, the diameter. Okay, so diameter is the independent variable, and of course that makes the circumference the dependent variable, right? Because c is dependent on d, the way the function is written. Now we could rewrite it using some algebra, and we could write an expression. In this particular case, we can write an expression for diameter in terms of circumference, but that's not the way it's written. So as it's written, it's written as a function for circumference in terms of diameter. So we're going to put diameter on the horizontal axis because it is the independent variable. Okay, always put the independent variable on the horizontal axis. All right, so let's plot these points that were given in the table. All right, so there you go. I've plotted all of those points and then connected them with a line. Okay, because I know that the diameter can vary continuously between 3 and 4 and maybe beyond, right? So, but I'm only showing diameters between 0 and 4. Now you notice I don't have 0 in the table, but I know that if the diameter is 0, then the circumference would be 0. So I plotted that point too for good measure. All right, so there you go. We've expressed we've described the circumference of a circle in terms of its diameter in words as a formula, a table, and a graph.